Hello, my name is Sina Sharifi, and welcome to my short presentation of our recent work titled Gradient-Regularized OD Detection Accepted to ECCV 2024. OD detection is the ability of a model to detect samples that are not from the original training distribution. However, closed-world neural networks often produce overconfident predictions on unknown images. The issue is that, in essence, the training algorithm results in energy manifolds such as the one shown in the bottom left image, where the model extrapolates out of its training data support. The goal is to, however, yield a score landscape more akin to the image on the right, where the model only makes predictions close to the in-distribution data support and understands when the data is out of distribution. Our OOD setting is as follows. We have a model that is trained on an ID dataset such as CFAR10. This dataset consists of 10 classes of real-world objects such as planes and cats. At test time, we present a new set of classes that are OOD. For example, SVHN dataset, which consists of street view house numbers. The goal is to have a scoring function that correctly assigns low scores to in-distribution images and high scores to out-of-distribution ones. There are many works in the literature that try to address this problem. Some works that are post hoc methods, that is, they work on a model that is already trained and find metrics that better distinguish ID from OOD. Other works train a network from scratch with the goal of OOD detection in mind. In these methods, we assume that there is an auxiliary outlier dataset available that is OOD, and we can utilize to train the model to better distinguish ID from OOD. To achieve our goal, we perform training time regularization for OOD detection. Using the following gloss, the first term promotes accuracy and the second term promotes OOD robustness. Our work builds on top of the well-known energy-based OOD detection method, and our regularization loss in this setting is shown in equation 2. The first term lowers the energy of ID samples until a desired threshold, and the second term increases the energy of the OOD samples. Prior works only focused on optimizing the value of the scoring function on data points, discarring the local information. However, intuitively, we say that the area in close proximity to an ID data sample most likely does not include any OOD samples based on the image, and vice versa, as the distance between the ID and OOD data tends to be large. To utilize such information, we leverage the gradient of the score function. By doing so, we promote that a desired OOD score for each sample is learned and that the network shows similar behavior in the local neighborhood around the sample. This behavior is better shown in the following picture. Intuitively, by using the first-order Taylor expansion, we know that if the norm of the gradient is small, the score manifold could be more stable. Consequently, we propose the following regularizer. Moreover, we propose an outlier sampling strategy. This is because the auxiliary data usually outnumbers the ID data significantly. Thus, exposing the model to all auxiliary data could cause bias due to the imbalance in the samples. On the other hand, by randomly selecting auxiliary samples equal to the number of ID data, we would not have fully utilized the auxiliary data. Thus, we employ a more informative sampling strategy. We cluster the data to M clusters, then for each cluster, we choose samples with lowest and highest energy score. This is because low energy samples are needed for energy loss and high energy samples are needed for gradient loss. To evaluate our method, we perform extensive experiments comparing the detection capability of our method with several methods on both on CFAR100 and ImageNet dataset. Greg is our gradient regularized training method, and Greg Plus is when we further utilize the informative sampling strategy to provide better samples. As the data shows, our method improves on the state of the art. We also study the utilization of our gradient regularization method on other state-of-the-art methods. As the table shows, by using our gradient regularization scheme, we can improve the OOD detection capabilities of the previous works. Thank you for your attention.